Rice University in the United States. So thank you for having me here, and I'm glad to share my research of using stable water isotope to study low clouds and shallow convective mixing. First of all, I want to thank my co-authors listed here. Thanks for their help and mentoring. So here are some pictures of marine low-level clouds. And low clouds are the clouds with the top pressure under 680 hectopascal. And in this study, we focused on marine low clouds and especially the trade cumulus or shallow cumulus. If we view the atmosphere meridionally, we can see that in the equator, we have very huge cloud tower due to deep convection. And in the subtropics, we have strong substance. And somewhere between this region, we have trade wind regions. We have shallow convection activities. So in this region, we have shallow cumulus, or because it's in trade wind region, we also call it trade cumulus. So this shallow cumulus comprise large parts of ocean surface. So it has very important climate effects. So because low clouds, they have high albedo, and also because they are in low altitude, they have high emission temperature. So basically their function is to cool down the surface temperature. In the future, climate models project that we will have reduced low cloud. So because low cloud reflects the radiation, the reduction of low cloud will amplify the surface warming. And we are eager to know that how much warming will due to the reduction of low clouds. So, however, current climate models have large uncertainties about the magnitude of the low cloud climate feedback. So that so we need better constraints on the role of the low cloud in modulating the surface temperature change in the future. So for governing the low cloud activity, one important physical process is shallow convective mixing. So shallow convective mixing is a mixing between the free troposphere and the boundary layer. So it exchanges the air between these two layers. These two layers have very different properties. So for example, free troposphere has low humidity and the boundary layer has high humidity. So the mixing between these two layers may decrease the water vapor gradient of these two layers and will have other climate effects. So how does the shallow convective mixing influence low clouds? So one prevalent hypothesis based on global climate models suggests this hypothesis. That is, the strong convective mixing will lead to reduced low clouds. So in the surface warming scenario, we will have more convective mixing. So the stronger convective mixing will make the free troposphere more humid and also dry the boundary layer. The drier boundary layer will suppress the formation of low clouds. So the reduction of the low clouds will further let more solar radiation reach into the ground and amplify the surface warming. So in contrast, when we have surface cooling, we may have weaker convective mixing and more low clouds. So this is a result based on GCM simulations. But there are another type of model, which is large eddy simulations. The large eddy simulations is very good to simulate cloud activities because it resolves very fine scale atmospheric motion and resolves the evolution of clouds, like shown, the figure shown here. So in their in large eddy simulation results, people find that there are no obvious changes of low cloud fraction due to the shallow convective mixing. So here we can see that GCM simulate reduced low cloud, but LES models shows no change of low cloud fraction. So we are wondering which one is the correct answer, and currently we don't have direct observations of convective mixing. So we need some observations of convective mixing. And we turn into water vapor isotopes because we are isotope people. We try to find out whether water vapor isotopes can help here. So here we're trying to use the satellite water isotope retrievals to estimate shallow convective mixing. So the basic idea is based on the vertical profile of water vapor delta D. So from this vertical profile, we can see that there is a large vertical gradient of delta D between the boundary layer and the free troposphere. The delta D in the boundary layer may be relatively constant, and then it will decrease in the free troposphere. And we are wondering that if we have strong convective mixing, the gradient between the boundary layer and the free troposphere will be decreased. So maybe we can use the vertical gradient of water vapor delta D to estimate shallow convective mixing. So this is the basic idea of this talk, and our goal is to justify this method. This is another example of the delta D profiles, but this profile is not from satellite, it's from aircraft observations, Eureka. So these profiles are the flight measurements over Barbados. So we can see that also in the boundary layer, like below 800 hectopascal, delta D is very constant, and then it gradually decreases into the free troposphere. In the strong convective mixing case, like this light blue, thick blue line, we can see that the gradient of delta D is relatively smaller. So our goal of this research is based on this idea, is using the vertical gradient of water vapor delta D to estimate shallow convective mixing. Our first research question is, can we use satellite retrievals to estimate shallow convective mixing? And then once we have the estimated convective mixing, we'll use them to study the influence of convective mixing on low clouds. So here is our estimation of shallow convective mixing from the satellite data. So this is the delta D gradient between the free troposphere and the boundary layer. So here the red color means there is more delta gradient, and which means strong convective mixing. The blue color means weaker convective mixing. So we can see that basically the spatial map shows in the warm pool region and the ITCZ, the convective mixing is stronger. And the movement, seasonal movement of the convective mixing follows the movement of the ITCZ. This is a result based on the satellite data tests. And we can see the result for another satellite data airs has a similar spatial pattern. So their results are consistent. So this is our estimation, but we want to make sure that our estimation actually really represent convective mixing, not something else. So we are trying to find other proxies of convective mixing to justify our estimation. Eventually, we don't have the real observations of convective mixing, and that's our research goals, but there are some proxies of convective mixing. So for example, this S index raised by Sherwood et al. 2014. So this is basically the combination of the difference of relative humidity and temperature between 700 hectopascal and 850 hectopascal. So this index is a proxy of convective mixing, and we can see the spatial pattern is similar to our estimation of convective mixing.
There is 2 minutes remaining.
Oh. And also we have a proxy of the updraft detriment rate. So we think that if we have strong convective mixing, we'll have a larger detriment in the middle of the atmosphere. So we've estimate the detriment rate from reanalysis data error 5 and compare it with our estimation of shallow convective mixing. So this is a correlation between the updraft detriment rate and the delta D gradient. So the red color means when we have higher convective mixing, we have higher updraft detriment rate. You can see they correlate very well in the shallow cumulus region. So this shows our estimation works well in the shallow cumulus regions. So that this shows we can use satellite retrievals to estimate shallow convective mixing. And then we see the influence of convective mixing on low clouds. So this is a composite of low clouds properties and environmental variables between high and low convective mixing months. So if we first look at the low cloud fraction, and if we focus on the shallow cumulus regions, we can find the signals are actually diverse. The signs are positive or negative. So this shows the relationship between convective mixing and low cloud fraction is diverse. And if we look at other environmental variables like surface temperature and relative humidity of free troposphere, we find that this is consistent with our previous hypothesis. When we have stronger mixing, we'll have moisture of the free troposphere, and that may reduce low cloud and amplify surface warming. We also look at the shallowness of low cloud, but I will skip here. So in summary, we explore that using satellite retrievals to estimate shallow convective mixing. And we find satellite retrievals can do that job. And we then use it to study the influence of shallow convective mixing on low clouds. And we find that relationship between shallow convective mixing and low cloud fraction is regionally dependent. And the strong convective mixing is associated with the moistening of the free troposphere. The next step, we will use the result to evaluate the simulations of GCM of this relationship. Thanks.